Chemistry Theory. This is EQ3.3, relative strengths of acids and bases. So here we'll look at relating the strength of an acid to the strength of its conjugate base. So relating that, some acids are better. Remember, we talked about acids as being something that donate a proton or an H plus ion, and a base as something that accepts an H plus or a proton. So some acids are better at doing this than others, and some bases are better at accepting protons than others. If we arrange the acids in order of their ability to donate a proton, we find that the more easily a substance gives up a proton, the less easily its conjugate base accepts a proton. Because if it easily gives it up, that means it's not going to want to go in that reverse reaction. Similarly, the more easily a base accepts a proton, the less easily its conjugate base gives up a proton. In other words, the stronger the acid, the weaker its conjugate base. And the stronger the base, the weaker its conjugate acid. Because remember, they're always paired up in acid-base pairs. Thus, if we know something about the strength of an acid and its ability to donate protons, we also know something about the strength of its conjugate base. The inverse relationship between the strengths of acids can be seen below. So this is a little schematic which you will get. And it's kind of a list of strong acids, weak acids, and very, very, very weak acids. And then vice versa, very, very weak bases, and then strong bases. So you can see it's vice versa here. So those acids that easily give up H's, those bases that easily accept H's are over here. So we'll use this table throughout this whole section. And again, you'll be able to access it. And it has the more common acids and bases on it. All right, we look at the next page. These acids and bases are grouped into three broad categories based on their behavior in water. So a strong acid, we can think of a strong acid as completely transferring all of its protons or H pluses to water, leaving no undissociated molecules. So 100% giving up its H plus ions. So it completely gives up its H pluses, leaving no undissociated parts at all. So its conjugate base has negligible tendency to be protonated, so the vice versa reaction is not going to happen because it strongly breaks down. So for example, if we look over here, HCl gives up an H plus and leaves Cl. Going backwards, the Cl wanting to accept an H and go this way, as we can see, it's weak. So they're vice versa. Strong acid has a weak base, strong base has a weak conjugate acid. A weak acid only partially breaks down or dissociates in aqueous solution, therefore exists in a mixture of acid and its conjugate base. The conjugate base of weak acid slows a slight ability to remove H plus ions from water. And then something that has negligible acidity, contains hydrogens but does not demonstrate any acidic behavior in water. So the chances of the acid wanting to give up an H is not going to happen. Something that is a weak acid is going to be a strong conjugate base. So the ions H plus and OH are respectively the strongest possible acids and strongest possible bases that exist in an aqueous solution. You can think of H plus transfer reactions as being governed by the relative abilities of the two bases to take those H plus ions. For example, consider the H plus ion transfer that occurs between HX. If H2O is stronger than X, because as we can see here, this is the scenario that happens. HX gives up its H and is left with X minus. The H2O becomes H3O. Vice versa, the hydronium ion gives up its H to X to become HX. So if the H2 in the forward reaction is a stronger base than the X in the reverse reaction, we would have the equilibrium line to the right. So if this is strongly accepting the H plus, it's going to exist in this direction. Whereas this strongly takes the H from here, it's going to lie to the left. Okay, so we're going to get into that and which way the equilibrium would lie mostly. When HCl dissolves in water, the solution consists almost entirely as this, because HCl is a really strong acid. So of course we could have H giving up its HCl giving up its H to become Cl, and the hydronium ion gets it. And of course the reverse reaction would be H3O giving up an H to become H2O and HCl. But since this happens easier most of it is going to involve HCl giving up its H and existing in this form. So whichever form the equilibrium is going to exist in, that's the direction of the shift. So H2O is a stronger base than Cl, therefore H2O requires the H. And then becomes the hydronium ion. That when X minus is stronger than H2O, the equilibrium would lie to the left because it would want to go this way. This situation occurs when HX would be considered to be the weak acid. So if we see that this is going to happen more frequently than this, then it would lie to the left in that direction. So for example, when we have this scenario, acetic acid plus H2O giving the acetate ion and the hydronium ion. So in this scenario, we can see to go from here to here, we must lost an H. And H2O, of course, accepts it to become H3O. Going backwards, this would happen. The hydronium ion would give up its H to the acetate ion, becomes acetic acid and H2O. But if we look over here, this is a stronger base than H2O. Therefore, it's going to remove H's from the hydronium ion and exist in this form more often. And that is why this is a weak acid, because it's combined with a strong conjugate base. From these examples, it can be concluded that in every acid-base reaction, equilibrium favors transfer of H plus ion from the stronger acid or to the stronger base to the weaker acid and weaker base. And we'll see how to in fact figure that out by using that chart that we saw on that first page and through some of these examples right here. All right, so if we look over here, first of all, we'll do what we did before. Identify the Bronsted-Lowry acids and bases and conjugate acids and base. So if we look over here, HSO4 becomes SO4. So these two are definitely related. And going from left to right, you can see that there's a donating of the H. Donate H. So that tells us that this is the Bl acid. And this, SO4 going to HSO4 would act like a base. So we say that's the conjugate base. And over here, CO3 to become HCO3, it's accepting an H. So anything that's accepting an H is Bronsted-Lowry base. And if I was going in reverse, HCO3 to become CO3 would give up an H, so that is going to be the conjugate acid. Okay, so all we have to do here is look at, we can compare the acids and then the base and see which one is stronger, this acid or this acid, and which base is stronger, this base or this base. So if we go back to that front page, let's look up HSO4. Let's see here. HSO4 is right here. And compare that to the other acid, HCO3. HCO3. There it is right here. So as we can see, the stronger the acid is further up the chart. So SO4 is the stronger acid. Stronger acid. Then over here, weaker acid. I'm going to do the same thing with the bases. CO3. Let's see where CO3 is. There's CO3. And compared to SO4. SO4, the stronger the base. So you can see here, the acid strength goes up this way. The stronger base is the one that's further down. So CO3 is stronger. CO3, stronger base, weaker base. And this is what you should see happening. So the stronger are on the same side and the weaker are on the other side. So if this is a strong acid and a strong base, that means that this is going to overshadow this. So the HSO4 will readily give up its H to CO3, and most of the reaction will exist on the product side. So the equilibrium lies to the right. All right, I think we'll stop the video there. You try some of the next examples here. I think there's two more examples. First, identify the Bronsted-Lowry acids and base, conjugate acids and bases, and see if you can use that chart to figure out what's happening. And then we'll go through them.